Number theory, lecture 8, and you asked for in which section is the exercise? Or what page?
Section 1.3, exercise 10.
1.3, exercise 10. Mhm. So this is section 1.3, exercise 10, which is on simple continued fractions. So the notation A0, A1, A2, up to A sub n means the fraction that you write is A0 plus 1 over A1 plus 1 over A2 plus 1 over A3 and so forth till you get to 1 over A sub n. So you have some complicated looking compound fraction. And the problem says to define
Wait, what problem is that? I don't think that's problem 10, right?
in section 1.3, this is problem 10. Why don't you read the problem that you're looking at?
Okay. Assume that the statement holds for some k, h sub k equals p sub k over q sub k.
I'm sorry, which number is that?
It says number 10.
On what page? Or in what section?
Let me see the page.
Because no problem would start with assume that it would have to explain what those numbers are. Let me just pause while you're looking for that.
It's on page 16. Okay. Yeah, I think that's the right number you're doing.
And read what is the first problem in that section that you're looking at? Problem number 1.
Problem number 1, let me see. Problem number 1. Use the Euclidean algorithm.
Okay, so that's section 1.3.
Okay.
And problem 10 starts by saying let A0 up to AN be a simple continued fraction.
Oh, yeah. I'm sorry.
Okay, so P0, we define P0 to be A0, P1 to be A1, A0 plus 1, and inductively we define P sub n to be AN Pn minus 1 plus Pn minus 2 for n greater than or equal to 2, or for little n between 2 and capital N. And we also define some numbers Q0 equal to 1, Q1 equals A1, and similarly Qn equals AN Q sub n minus 1 plus Qn minus 2, again for n between 2 and capital N. And we want to prove that this continued fraction is equal to up to little n is equal to Pn over Qn for all n between 0 up to n. Okay, so So what we want to prove is, if you want to calculate this compound fraction, this continued fraction, step by step, it's always going to be given by this sequence of numbers. So let's just check what this means. So the simplest case is n equals 0. When n is 0, we're looking at the continued fraction a0, which is a0, which is the same as a0 over 1. And a0 is p0 and q0 is 1. So this is p0 over q0. So this statement is correct for n equals 0. Let's check this statement for n equal 1. When n equals 1, we have a0, a1. That continued fraction is a0 plus 1 over a1. If we put this over, if we just add these two fractions, this is a0, a1 plus 1 over a1. But a0, a1 plus 1, that was defined to be p1. And a1 is defined to be q1. So again, this is p1 over q1 for n equal 1. So this statement is true for n equals 0 and n equal 1. So we want to prove the result in general. By induction. So suppose, so this is a proof by induction. Suppose if you have n between 0 and capital N minus 1, and this continued fraction a0, or let's put it like this, suppose n is between 1 and capital N, and the continued fraction a0, a1 up to a sub n minus 1 is equal to pn minus 1 over qn minus 1. So we assume this is true. And then we must consider the continued fraction where we add one more term, a0, a1, an minus 1, a sub n. So what is this? This is a0 plus 1 over a1. It goes down to plus 1 over a sub n minus 1 plus 1 over a sub n. All right. So what is that? Let's see. So I know what the continued fraction where you go up to n minus 1 is, and the continued fraction when you go up to n is this part plus this. But this expression is the same as, let's see, a0 plus 1 over a1 plus 1 over, and now it goes down to 1 over, and what is this? This is, if I put this over, if I just add these two fractions, this is an minus 1, an plus 1 over an. So let's see. Let me try and see if I can write this in an easier way. Suppose we look at Pn over Qn. So Pn is what? Pn is An, Pn minus 1 plus Pn minus 2, and Qn is An, Qn minus 1 plus Qn minus 2. Let's see, what is this? This is see. So I'm trying to find an easy way to express this. Let's just look at, let me look at an example just to see, just to make this a little bit more concrete. Okay. I'll just write down a continued fraction at random. Suppose I look at the continued fraction 2, 3, 4. So what is this? This is 2 plus 1 over 3 plus 1 over 4. That's what this continued fraction is. This computed. This is 2 plus 1 over 3 plus 1 over 4 is 13 over 4. So this is 2 plus 4 over 13, which is equal to 30 over 13. So if I have the continued fraction 2, that's equal to 2. And if I have the continued fraction 2, 3, that's 2 plus a third, which is 7 over 3. So let's look at the sequence of numbers, the P0, P1, P2. So P0 is A0, which is the first number, which is 2. P1 is A1, A0 plus 1, which is A1 is 3, A0 is 2, plus 1 is 7. And P2, by our rule, is A2, P1 plus P0. A2 is 4, P1 is 7, plus 2, that's equal to 30. So these are the numbers P0, P1, P2. Q0 is 1. Q1 is A1, that's 3. Q2 is A2, Q1 plus Q0. A2 is 4 times 3 plus 1 is 13. So if we look at, this is the continued fraction with just one term, 2. 2 is equal to P0 over Q0, 2 over 1. 2 comma 3, 7 over 3, is equal to P1 over Q1, 7 over 3. When we have terms A0, A1, A2, 30 over 13, this is equal to P2 over Q2. So this is exactly correct in this example, right? And how could we get from one case to the next in this? Let's see. So suppose A0, A1 up to A sub n minus 1 is equal to Pn minus 1 over Qn minus 1. So how can we write A0, A1, An minus 1 up to A sub n? So this is
Professor, I'm confused. Where you got these numbers?
These numbers here?
Yeah.
So here I have my continued fraction, 2, 3, 4. So this is an example. That's my continued fraction. In this continued fraction, the first number, A0, is 2. The second number, A1, you see is 3. The third number, A2, is equal to 4. Those are the numbers. This is our notation. When you write a continued fraction, the first number is A0, the next number is A1, the next number is A2, and so forth. So these are the numbers A0, A1, A2. All right. How are the numbers, the P's and the Q's defined? P0 is defined to be A0. In this example, A0 is 2. P1 is defined to be A1, A0 plus 1. That's 3 times 2 plus 1, that's 7, and so forth. I'm just plugging these numbers into the formula.
Okay, I understand. Thank you.
Okay. So, and how did we get? We got, for example, that 2, 3, which is 2 plus 1 over 3, is P1 over Q1. 2, 3, 4 is 2 plus 1 over 3 plus 1 over 4, right? I have to show that's equal to P2. I mean, it is equal to P2 over Q2 because I actually did the calculation. I actually did the calculation. Question is, how do we get to prove this in general? So one way to see this is the following. If I have A0, A1 up to A sub n minus 1, A sub n, these can be any numbers. They don't have to be integers. This is A0 plus 1 over A1 plus 1 over A2 plus 1 over AN minus 1 plus 1 over AN. So if I think of this as a single number, this is exactly the same as A0, A1 up to the number just before that would be A sub n minus 2. And I can replace AN minus 1 by AN minus 1 plus 1 over AN. Right? This is just like a continued fraction with one less term, but where the last term is AN minus 1 plus 1 over AN. So if I'm computing my sequence P0, P1 up to P sub n minus 1 for this, what do I get? I have the same numbers for P0, P1 up to P sub n minus 2, and the new P sub n minus 1, we'll call it P sub n minus 1 prime, would be equal to AN minus 1, that's this, AN minus 1 plus 1 over AN, PN minus 2 plus PN minus 3. And the new Qn minus 1 prime would be equal to AN minus 1 plus 1 over AN, Qn minus 2 plus Qn minus 3. Because we're assuming that this statement is correct when you go from 0 up to n minus 1. So my fraction, A0, A1 up to AN, is equal to Pn minus 1 prime over Qn minus 1 prime. That's equal to AN minus 1 plus 1 over AN, Pn minus 2 plus Pn minus 3 over AN minus 1 plus 1 over AN, Qn minus 2 plus Qn minus 3. And I can multiply through by AN to get rid of this denominator. I get AN minus 1 plus 1 times Pn minus 2 plus Pn minus 3. I'm just multiplying through by AN minus 1 plus 1, Qn minus 2 plus Qn minus 3. And let's see, what is that equal to? So this, let me just look at this numerator. This numerator, if I expand it, is AN minus 1, Pn minus 2 plus Pn minus 3 plus Pn minus 2. And let's see, oh, sorry, when I multiply through by AN, I get AN here. So I can, so it's AN minus 1, Pn minus 2 plus AN, Pn minus 3, that's this, plus Pn minus 2. But this is Pn minus 1, which is exactly how we define Pn. So the idea of the proof is, if you have this continued fraction from A0 up to AN, you can think of this as a continued fraction with we only go up to an minus 1, but the new n minus 1 is equal to this. And if you then use the formula by the inductive formula, if you use the fact that this is Pn minus 1 over Qn minus 1 and work out the arithmetic, you get the result. Right? So, so some problems are easy, some problems are hard. This problem is hard. But of course, it's good to have hard problems because that sort of forces you to think a little bit. But the best way to understand what's going on is to work out particular examples. So here I just took at random the example 2, 3, 4, and I checked that and everything was correct. So if you want to understand what's going on in the proof, the best thing to do is just to write down another continued fraction at random, just make one up with 3 or 4 or 5 terms, compute the PNs and the QNs, and see that they give you exactly what you're supposed to get. Okay, so there are some problems that you really need to think about a lot, and this is one of them. Problem number 11, the next problem in this set, is to work out the continued fraction 1, 2, 2, 2, 2, 2, 2, and compute what you actually get to a certain number of decimal places. So let me actually do number 11.
Can I see the last page you just did?
Sure.
Okay, I'm done.
So number 11, we have the continued fraction 1, 2, 2, 2, 2, 2. So let's compute this. So in this case, A0, the first number is 1, and all the other numbers, A1, A2, 1, 2, 3, 4, 5, up to A6, they're all equal to 2. So if we compute the sequence of numbers, P0, P1, P2, P3, P4, P5, P6, and Q1, Q2, Q3, Q4, Q5, Q6. What are these numbers? So P0 is A0, is 1. P1 is A1, oh, A0, that's 2, plus P0, that's 3. P2 is A2, P1, plus 1, which is 7. Right? Let me just double check that everything is right. So P0 is A0 is 1. P1 is A1, A0 plus 1 is 3. P2 is 2 times 3 plus 1. P3 is 2 times P2, 7, plus P1, that's 17. P4 is 2 times 17 plus 7 is 41. P5 is 2 times 41 plus 17. That's 82 plus 17 is 99. P6 is 2 times 99 plus 41. That's equal to 198. I think that's 239, but I'm not making too many mistakes. You need to check me, of course. Q1 is, sorry, forgot Q0. Q0 is 1. Q1 is A1, that's 2. Q2 is 2 times 2 plus 1 is 5. Q3 is 2 times 5 plus 2 is 12. Q4 is 2 times 12 plus 5 is 29. Q5 is 2 times 29. That's 58 plus 12 is 71. Q6 is 2 times 71 plus 29. That's 142 plus 29 is 171. So if I did my arithmetic correctly, what are the fractions that we get? P1 over Q1 is 3 over 2. P2 over Q2 is 7 over 5. P3 over Q3 is 17 over 12. P4 over Q4 is 41 over 29. P5 over Q5 is 99 over 71. P6 over Q6 is 239 over 171. Right. Let me write these as decimals.
Professor,
Yes. Go ahead.
for Q5 for Q4 it's 29. I mean Q5 I got 70.
So 2 times 29. Oh, sorry, 58 plus 12 is 70. Thank you. So this should be 70. So Q6 is 2 times 70 plus 29. That's 140 plus 29 is 169. Thank you. So it says compute. Let me compute these numbers to 5 decimal places. So 3/2 is 1.50000. 7/5, these I can do in my head, 14000. 17 over 12. Take my calculator. 17 divided by 12
1.416667
is 1.41667. 41 divided by 29 is 1.1379. 99 over 70 is 1.414 285, so 1.41429. 239 divided by 169 is 1.41420. So let's see, and you look at these numbers, this from here, as you go from one to the next, this goes down, this goes up, this goes down, this goes up, this goes down, and I said compare it to the square root of 2. So square root of 2 is 1.41421. So this is really very impressive. This, when I compute just this this continued fraction, this gives me a fantastically good approximation to the square root of 2 as a fraction. I mean, you would, if you had to guess, like, what is the best fractional approximate, if you want to write approximate the square root of 2 as a fraction, what's the best you can do? Up to, I mean, obviously you can get as close as you want if you want to make the denominator bigger and bigger. But with a fairly small denominator, 169, this fraction is within 1/10,000th of the true value for the square root of 2. This is a fantastically good approximation to the square root of 2. Okay. And there is a a very important theorem in mathematics that says if you have an irrational number like the square root of 2, irrational means you cannot write it as a fraction. Square root of 2 is not a fraction. It's irrational. But if you want to find the best rational approximation to this number, with the denominator not too big, it always comes from writing what is essentially what you would call the continued fraction for the square root of 2. Square root of 2 will have like an infinite continued fraction. But if you stop it at any point and you compute the rational number you get, up to that size denominator, this is always the best rational approximation to this number. That is a truly miraculous property of continued fraction.
Oh.
So this is just a very nice example of some mathematics that you should know. Just as an exercise, and I don't think I've done this yet, but just as an exercise for one's general knowledge of number theory, let me just say that a real number theta is called irrational if it cannot be written as a fraction. A rational number is a fraction. A number is irrational if it cannot be written as a fraction. And an ancient question is every number a fraction? Or do irrational numbers exist? And this was solved by the Greeks. And they gave a very explicit example. The square root of 2 is irrational. And the proof uses the fundamental theorem of arithmetic. The fundamental theorem of arithmetic says every positive integer is uniquely expressible as a product of powers of prime numbers. So we're going to use that to prove the square root of 2 is irrational. And the proof will be by contradiction. How do you prove something by contradiction? Assume the opposite. What is the opposite of saying that the square root of 2 is irrational? The opposite is saying the square root of 2 is rational. What does that mean? That means the square root of 2 can be written as a fraction, a over b. And what can we say about this fraction? First of all, square root of 2 is positive. So we can write a and b, they're either both positive or both negative, so we write them both as positive. And if we have any common factors, we can do between the numerator and denominator, we can cancel them. So we can write this fraction in lowest terms. Lowest terms means the greatest common divisor of a and b is 1. If there is some common divisor of a and b, we could cancel it. So if we assume the opposite of what we want to prove, if we assume that the square root of 2 is rational, then the square root of 2 is a fraction, a over b, where a and b are positive integers that are relatively prime. So square this equation. So the square root of 2 squared is going to be a over b squared. If you square the square root of 2, you get 2. And if you square a squared over a over b, you get a squared over b squared. So we get this equation. Or if I just multiply through by b squared, a squared is equal to 2b squared. Okay. So everyone has to look at that, and if there is a problem, let me know.
Okay. Professor,
Yes,
hello. Why is the GCD of A comma B equal 1?
because if they have a common denominator, common divisor, you can cancel it. I mean, if A were equal to 7 times some number and B were equal to 7 times some number, then when you cancel them, and you get
Oh,
A prime over B prime. So whenever you have a fraction, you can always put it in lowest terms, right? I mean, that's what you did in elementary school when they taught you fractions. You can write a fraction in lowest terms. That means the numerator and denominator have no common divisor. You can always can't divide it out. So to say that a fraction is in lowest terms means exactly that the greatest common divisor of numerator and denominator is 1.
okay.
Right. So no problem, just cancel. So if I have this equation and I square it, I get 2 is a squared over b squared, or a squared equals 2b squared. Which means what? It means 2b squared is even. That means a squared is even. And if you take a number that's odd and you square it, you get an odd number. If you take a number that's even and you square it, you get an even number. So if a squared is even, that means a is even. Right? If a were odd, a squared would be odd. Odd times odd is odd. So a even means a is equal to 2 times capital A. That's the definition of an even integer. It's twice an integer. So a squared is 2 capital A squared. That means square this, you get 4 capital A squared. A squared is equal to 2b squared. Right? So you have 4 capital A squared is 2b squared. Divide by 2. 2 capital A squared equals b squared. Which means b squared is twice an integer. B squared is even. And if b squared is even, b is even. And that's a contradiction because I showed that a is even, and now b is even, but I took a and b to be relatively prime. They can't both be even. If they were both even, you could divide out by 2. So contradiction. And that's the proof. So if you haven't seen this before, this is really one of the high points in the history of mathematics, that the proof that irrational numbers exist, and in particular that square root of 2 is irrational. In fact, the legend is that the Greeks believed in somehow the harmony of the universe, and somehow there could not be an irrational number. Every number should be rational. An irrational number would mean something was, from their sort of philosophical point of view, something was out of whack. And then there was a kind of mathematical cult around Pythagoras. And the people in the Pythagorean cult discovered that square root of 2 was irrational. And this was so disturbing, they wanted to, it was sort of like they classified it top secret so it wouldn't be revealed to the public at large. But one of the Pythagoreans somehow told people about this. He discussed it. And to punish him, they say, they put this guy in a boat, took him out into the Mediterranean, threw him over, and let him drown. So who would have thought mathematics could be so dangerous to life and limb? But that is the legend of this. But the fact that the Greeks discovered the irrationality of numbers And this was really disturbing to their kind of metaphysical view of the universe, is historically correct. And this is a very simple, very beautiful proof that the square root of 2 is irrational. Any questions about this? This is really something you should know. And in fact, if any of you end up as math teachers in junior high school or high school, this is really something you could teach your students, because it really uses just elementary arithmetic. All it comes down to is the fact that the product of two odd numbers is odd and the product of two even numbers is even. You could ask, what other numbers are irrational? And a similar kind of argument can be used to prove that, for example, square root of 3 is irrational. This proof's a little bit more complicated than the square root of 2, but the basic idea is the same. So the proof will be by contradiction. Again, suppose you can write the square root of 3 as a over b, where a and b are positive integers, and you can cancel any common factors. So the greatest common divisor of a and b is 1, right? You can write square root of 3 as a fraction reduced to lowest terms. So if you square this equation, square root of 3 squared is 3. That's a over b squared, which is a squared over b squared, right? And again, just as we did before, multiply by b squared, you get a squared is equal to 3b squared. Right? So a squared is a multiple of 3, right? Now, that's sort of like, so a squared is a multiple of 3. A squared is a multiple of 3. I claim this implies that a is a multiple of 3. So this is similar to what I proved a few minutes ago about 2. If a squared is even, then I prove that a is even. Here, I claim that if a squared is divisible by 3, then a is a multiple of 3. A is divisible by 3. So how can we prove that? This is the proof of the claim. Take the number a. If you divide it by 3, it's 3 times q plus the remainder, where the remainder is 0, 1, or 2. So if the remainder is 1, a is 3q plus 1. So a squared is 3q plus 1 squared. That's 9q squared plus 6q plus 1. This is 3, factor of 3 out of these first two terms, or 3q even, 3q times 3q plus 2 plus 1. So a squared is 3 times something plus 2. So this is not divisible by 3. So if a is a multiple of 3, sorry, if a is 3q plus 1, it's not a multiple of 3. Suppose this remainder were 2. Then a is 3q plus 2. If you square that, a squared is 9q squared plus 12q plus 4. What is that? I can factor out a 3. I get 3 times 3q squared plus 4q plus 4. 4 is the same as 3 plus 1. So if I factor out a 3 from these first three terms, I get 1 plus 1. So if r is 2, if a is of the form 3q plus 2, then a squared is 3 times something plus 1. Again, it's not divisible by 3. If you divide a squared by 3, you get a remainder of 1. So a is 3q plus r. R is 0, 1, or 2. But if r is 1 or 2, a squared is not a multiple of r. So therefore, a is 3 times q. A has to be a multiple of q. So then we take that and plug it into this. A is 3 times q squared plus 3 equals 3b squared. If I square this, this is 9q squared equals 3b squared. Divide by 3, 3q squared equals b squared. So b squared is a multiple of 3. So 3 has to divide b. But I just showed 3 also divides a, and that's a contradiction. Because we took a and b to be relatively prime. So the square root of 3 is irrational. Yeah, that's very nice. And if you want a nice exercise, this is not homework, but this is just a nice exercise to understand what's going on. Prove square root of 5 is irrational.